Hello everyone. In the previous class we considered the free electron gas where we consider it as a one-dimensional problems where we consider the flow of electrons where it is confined in a particle in a box kind of problems where this is the things we consider where this is the electron which is inside this box of length L 0 to L, and the potential inside this box is V is equal to 0, and we treated as outside the box the potential is 0, so that the particle will be always inside the box. So the probability will be 1 if we consider within the length 0 to L length. So when we consider it as three-dimensional problems where electron can be moved along three different directions. So in that case we have to consider it in a similar way. Instead of this particle in a box, it will be a particle, the electrons is confined within a three-dimensional rectangular box. So the problem will be like this where we have to consider three dimensions. One is Lx, along the length of the dimension along x direction is Lx, and let's say this is Ly. So this dimension is, this length is Ly, and this is our z direction. So now the particle is confined within this rectangular box, so that in similar fashion this inside this box V is equal to 0, the potential is 0 inside the box, so that the probability of finding inside the box should be 1, whereas outside the box this will be V is equal to infinity. Similarly, that is the wave functions inside the box psi is not equal to 0, whereas outside the box psi is equal to 0. So just like we did in the case of one dimensional, in this case we have to consider the three-dimensional Schrodinger equations, that is minus h cross square by 2m into dou square by dou x square plus dou square by dou y square plus dou square by dou z square into our wave function, that is psi kr is equal to the energy eigenfunction, that is En psi k of r. So let it be the equation number 1. Now the solution of this wave function should be of the form, if you consider the similar way, this is confined in this box of length Lx along s direction, and along y direction is Ly, and along z direction it is Lz. So the solution will be of same format if you consider the box in a real space. So the solution will be like this: a sine nx pi x by Lx sin ny pi y by Ly sin nz pi z divided by Lz. So these are the dimension along three different dimensions, and nx, ny, nz are the these are the integers. Nx, ny, nz are the integers. So this will be a plane wave. So solution of this form will be a plane wave. We can written in wave vector format, that is psi k of r is e raised to ik dot r, where k is the wave vector. So the k is, the wave vector k is kxx plus kyy plus kzz. Also in the real space, this r can be in the Cartesian format. This will be xx plus y plus z. So that this e raised to ik dot r, the solution e raised to ik dot r, we can write it as this is the one, that is e raised to I kxx plus kyy plus kzz. So let it be equation number 2. Now you can apply this equation number 2 here. Before that we have to consider the boundary conditions. Just like the previous case, in this case also there is a periodic boundary conditions where these are the ionic sides. So the wave function at this at this point, which are at a distance, similar distance away from the ionic side. So this will be having these two functions should be the same. So that means this has to obey the periodic boundary conditions, that is psi k of x, if we consider along x direction, so psi k of x should be equal to psi k of s plus L. So if you consider here the same thing here, this has to be the left hand side should be e raised to I k dot x should be equal to e raised to I k dot x plus L. If this has to be same, e raised to I k dot L should be equal to 1. What is e raised to I k dot L? That is e raised to, sorry, in this case, since it's along s direction, it is Lx. So we can write it as e raised to IKL. So since both are, we are considering only the x dimensions along the wave vector also, so that e raised to IKXL should be 1. So that means the KXL, what will be the KXL? What is e raised to, sorry, there is an e raised to I. So e raised to I theta is cos theta plus I sin theta, that is cos KXL plus I sin KXL is equal to 1. So this we have to eliminate this imaginary terms, because this is not here. So this term is equal to 0. That means cos kxl is equal to 1. So that corresponds to kxl is equal to n times 2 pi, where n is equal to 0, 1, 2, etc. So kx is n times 2 pi, or kx is equal to n 2 pi by L, where n is equal to 0, 1, 2, 3, etc. So these are the, according to the periodic conditions, the values of kx should be n 2 pi by L, Lx. So this is Lx. Similarly, ky should be n 2 pi by Ly, and kz should be n 2 pi by Lz. Now we substitute the plane wave solution in our three-dimensional Schrodinger equation, so that this will be minus h cross square by 2m into dou square by dou x square plus dou square by dou y square plus dou square by dou z square into this term, that is e raised to ikxx plus ky y plus kz z, which is equal to, the right hand side is en, this is e raised to I kxx plus ky y plus kz z. Now we can differentiate these terms, second derivative of these terms or individually, so that this will be minus s cross square by 2m into this term will be here, that is e raised to ikx plus ky y plus kz z into when we take dou square by dou x square of e raised to this term. So you only need to differentiate the first terms, that is ikx all square. Similarly, when you take second derivative of y, this will be plus iky all square plus ikz all square is equal to en e raised to I kxx plus kyy plus kz z. So these two terms are common. So these two terms, you can see that these are commons. So that I square, this is minus h cross square by 2m into minus kx square plus minus ky square plus minus kz square is equal to en. or this energy eigenfunctions En is equal to h cross square by 2m into kx square plus ky square plus kz square, or this is h cross square k square by 2m. So these are the energy eigenfunctions. So this is equation number 4. Now we are treating the problem in k space, that is the momentum space. So in a Cartesian coordinate systems, if there are n electrons, so in a k space these are represented by points in k space. So for that we consider this Cartesian problem is converted into the k space. So this will be a 3D sphere. So this can be considered as a 3D sphere. The problem is reduced to a 3D sphere where the radius of the sphere is kf, that is the wave vector kf Fermi corresponds to the Fermi energy, where the surface of this is the radius kf, and the surface at this point the energy will be ef, which is the Fermi energy. So these are the kf is the wave vector and ef is the corresponding energy at the surface of the sphere, which is the Fermi energy. Now we are considering different points in k space. So we have derived the expression for kx by applying the periodic boundary conditions, that is plus or minus n 2 pi by L. So these are the according to the periodic boundary conditions. So that is in 3D. In 3D, the values of kx are 0, plus or minus 2 pi by L, plus or minus 4 pi by L, etc. Similarly, ky is 0, plus or minus 2 pi by L. So these are Lx. Along x direction is Lx and along y direction is Ly, plus or minus 2 pi by, sorry, this is 4 pi by Ly, etc. And kz is 0, plus or minus 2 pi by Lz, plus or minus 4 pi by Lz, etc. So these are the values of kx possible according to the boundary conditions. So we can see that the intervals, so within 0 to 2 pi by Lx, there exists a kx value. Similarly, within between 0 and Ly, between 0 and 2 pi by Ly, there exists a ky value, and between 0 and 2 pi by Lz, there exists a kz value. So we have, so this problem, so if you consider one point here, which is another rectangular, so if this is another rectangular inside this k space with dimensions kx along x direction, ky along y, and kz along z directions. So within that rectangular box, which is of dimensions kx, ky and kz, there exists a k values. So there exists a k value within that particular box. So since the dimension along x direction, y direction and z direction of this particular rectangular box is 2 pi by L. So within a volume of 2 pi by L all cube, there exists a k values. So for a particular k values, there exist two electrons, one with up spin and one with down spin. So there can be two electrons corresponds to 1 k values. So if you want to know the total number of electrons n, that will be we have to consider the volume of the sphere, that is 4 by 3 pi k f cube, that is the volume of the whole sphere. So the volume of one of these rectangular boxes that is 2 pi by L all cube. So that is the volume occupied by one particular k value. So we are dividing the whole sphere volume with a particular k value problem. Then inside a 1 k value there exists 2 electrons. So this has to be multiplied by 2. So this is the total number of electrons in k space. To reduce this one, 2 into 4 is 8. There is another 8 here, that is 2 raised to 3. So we can cancel those terms. So finally we get 1 by 3 into this L cube will go to the numerator, L cube. Then there is a kf cube term divided by pi square, because in this pi cube one of the pi will be cancelled with this pi, so this will be pi square. So this is L cube by L cube kf cube by 3 pi square. So for a real space problems where we consider a rectangular box of dimension L along x, y and z directions, this L cube represents the volume of the cube. So we can replace this one as consider it as a volume of the cube. So now we are considering dimension along all three dimensions are equal. So this will be VKF cube divided by 3 pi square, where k is the wave vector corresponds to the Fermi energy, that is the radius of the or sphere in k space. So from this we can get the expression for kf, that is 3 pi square n divided by v all raised to 1 by 3. So this is the value of kf using this one, where n is the total number of electrons. So total number of orbitals here, total number of orbitals. Now the expression for Fermi energy EF from our previous derivation we found that this is h cross square kf square divided by 2m. So the Fermi energy will be h cross square kf square by 2m. So now you can substitute for kf here. So the expression for Fermi energy will be h cross square by 2m into 3 pi square n by v all raised to 2 by 3. So 1 by 3 all raised to 2 will be 2 by 3. So this is the expression for Fermi energy. Here the Fermi energy is represented in terms of n by v, that is the number of electrons per unit volume, that is the density of carriers inside the orbitals, n by v. Now we have the expression for kf and expression for Fermi energy. Now the velocity of electrons at the surface of the sphere, that is the Fermi velocity, that can be written as Vf. So expression for Vf is, that is mvf is equal to h cross kf. So Vf is h cross kf divided by m, that is h cross by m into value of this one is kf is 3 pi square n by v all raised to 1 by 3. So this is the expression for Fermi velocity, that is the velocity at the surface of the sphere. Now we need to find out the expression for density of states. So the density of states is defined as the number of electronic states, the orbitals per unit energy state. So density of state is defined as the number of energy states available within a unit energy interval. So that is dn by d. So we can get the expression for number of orbitals from this expression, that is n, which will be v by 3 pi square into 2mef by h cross square all raised to 3 by 2. So this is the expression for n from this expression, from the expression of Fermi energy. We can put an equation number here, I think it is 6, in order to get the expression for density of state, you can differentiate this one with respect to energy. So this will be v by 3 pi square 2m by h cross square all raised to 3 by 2 into when you take the differential with respect to this one, that is 3 by 2 EF raised to half. So this is the expression for density of states. So from this expression we can see that generally the density of states which is proportional to e raised to half. So this is how the density of state is related to energy in general. So this is proportional to e raised to half. So if you plot the density of states, that is along y directions versus energy along x directions, the curve will be something like this. This will be something like this. And if at Fermi energy, it will be here. it is completely spilled. So this is corresponds to when the temperature is 0 Kelvin. So of when the temperature is increases, this function the more electrons the carriers can shift to the higher levels of energy, so that this will be curve will be like this. So some of the electrons will be moving to the higher levels. So this is how density of states is related to energy. In today's class, we consider the electrons flow in a 3 dimensions. We consider the time independent Schrodinger equations, and we got the energy eigenvalues, and we got the values of k values, that is the wave vector in k space. So we found that it is discrete. Then we consider the problem in k space, the momentum space, where the problem is equivalent to a sphere. So this is represented as sphere, and the number of electrons in the real space is here it is treated as points in k space. And we found that the k can only have this kind of values, that is according to the boundary conditions. And within a box of 2 pi by L all cube, within that dimensions there exist a k values, and for a corresponding k values there can have 2 electrons with upspin and downspin. Then we got the expression for total number of electrons, orbitals, allowed orbitals. From that we got the expression for Fermi energy using our relation energy is proportional to k square, that is h cross square k square by 2m. Then for corresponds to kf, that is the wave vector corresponds to the Fermi energy. From that we got the expression for Fermi energy. And finally using the value of n, we got the values of density of states, and we found that the density of state is proportional to e raised to half. So this is how the density of state is related with energy. Okay, thank you.